Good morning, chemists. It is a balmy -9 degrees right now for me. So I hope it's better weather somewhere where you are in the morning, in the afternoon, or in the evening. All right. This lecture is going to be on a basic review of everything you were supposed to bring to me from Chem 1 or from Organic Chem 1. So let's go to my wonderful handouts. All right, it's long and I'm very proud of it. So I wrote this over the weekend. So it is literally the basics of everything you are supposed to bring from OChem 1 with you. And then there's one on reactions and functional groups, and then I have a separate one for structure and spectroscopy. Now, I'm not going to go through the entire thing in detail. I'm going to kind of highlight it, but I am going to detail the reactions that you're supposed to know because the first portion of organic chemistry 2 is all about reactions. So we need to get through every reaction, bring everything from OChem 1, and then we get to start synthesizing things. All right, so let's do a brief review of OChem 1. All right, the parts of the reaction, the nucleophile, make a pencil here. Remember, the nucleophile is the thing that is attacking. The electrophile is the thing that gets attacked. And then they have different strengths. And then I wrote all the different strengths that I had for you in here. But generically, negatives are always better than lone pairs, which are better than pi bonds, which are better than sigma bonds. And then here's the jolly rules for it. If it's negatively charged and it has a pKa of greater than or equal to 15, remember that's a strong base and that likes to do elimination. And then the good ones are negatively charged with no resonance, and the fair and the weak. And do not forget the alkynide ion is an amazing nucleophile because it has no steric hindrance. All right, my little mantra. Nucleophiles can do two things. They may rip off, usually hydrogens, or they may attack, usually carbons. So that's going to lead us to the types of reactions. So if they're ripping off hydrogens, that's going to be some kind of acid base. It's either protonating, it's deprotonating, something along that lines, or it's eliminating. If it's attacking carbons, then it is substituting or adding. And your electrophiles are just as important, and their role is positives or protons, or remember just empty orbitals, are awesome electrophiles and love to be attacked. And then polar bonds, specifically those that have leaving groups. Your leaving groups have to come off as a stable base. And again, I give you a wonderful little blurb right there for your leaving groups. And iodine, as far as the halogens are concerned, is usually our best one. But remember, we have other types of leaving groups that we mate, that's sulfonates and things like that. All right. These solvents come into two forms. You've got polar and you've got nonpolar. Your polar can be protic, which means it can hydrogen bond, or it can be aprotic, but I break that further into ones that can participate in hydrogen bonding and those that can't participate in hydrogen bonding. Now, the reason I give you this great big solvent list is sometimes it's nice to just have a list somewhere. This is not on the reference sheet because maybe I'll put it there in the future, but it's kind of long and we don't use it that often. But here's just the common solvents, their formula, their boiling points, their densities, and then their dielectric constants or how polar they are. Again, you're not going to memorize those, but we will refer back to those quite often. All right, the types of reaction, the big four. So substitutions, eliminations, additions, and rearrangements. Very generically, substitutions is when you have a leaving group plus a nucleophile and it gets substituted and it kicks off the leaving group. Elimination, instead of attacking the carbon, it'll go for a beta hydrogen, forms the pi bond, and kicks out the leaving group. Addition breaks a pi bond but this one's two steps. So first you have to make a carbocation, and then the other portion comes and attacks it. So this one has the Z on it, and that one has the hydrogen on it. All right. And then the rearrangement. Now, we've seen this most often with carbocations, but it can happen with others. So I'm going to do keto-enol tautomerization for you. And let's see. Let's say we have an alkene and there's an alcohol sitting on the alkene, which is a no-no. So remember, alcohols are not on sp2 hybridized carbons. So this is, if you will, a visual of a rearrangement. This is going to rip off, okay, the pi bond's going to rip off the hydrogen, which is going to donate its electrons down to make another one. And what you really have is a carbonyl, in this case, a ketone in disguise. But that's just an example of rearrangement. And if I had a carbocation, remember the jolly simplification rule is you may go one direction adjacent, but you do have to make it more stable. So if I went this direction right here, that's not going to make it any more stable. But I could migrate this hydrogen over to there, and I would be left, whoops, with a tertiary carbocation, which is more stable. So both of those are examples of rearrangements. Don't forget my extra two. Okay, everything will fall into the big four, but sometimes it's just not obvious or it's not important to go that detailed. So if you ever protonate or deprotonate, okay, that's just generic acid-base chemistry. And then we went over oxidation and reduction pretty deeply on the last handouts. So don't forget those. Just some terms as far as mechanisms go. Intermolecular, okay, just like in Gen Chem. Inter means between molecules. Intra means on the same molecule. So everything I've done up here, that was inter, T-E-R, molecular. Well, if you want to do an intra, it has to be on the same molecule. So let's put a leaving group. And I know it looks silly, but the leaving group and the nucleophile are on the same molecule, and that one is an intra. So 1, 2, 3, 4, 5, 6. So that would make space, space, space. 1, 2, 3, 4, 5, 6 with the nucleophile in between. So that's what I mean by intramolecular. All the pieces are on the same molecule. All right. Stepwise means it takes steps. Concerted always goes through an intermediate. So the addition reaction up here, let me change colors. The addition reaction went through an intermediate, and in this case, it was a carbocation, so it took two steps. So this one was stepwise, where the substitution was concerted because it all happened at once. Okay, so just some terminology there for mechanisms. Syn versus anti. Syn is the same side, anti is the opposite side, and we've seen the terms syn periplanar and anti-periplanar. In that case, the leaving group is completely opposite. We'll say the hydrogen, but it has to be in the same plane. So that one would be called anti-periplanar. And this one would be called syn-periplanar. And this is how we got the cis and transalkenes. And then we went on to talk about Zaitsev. One more is stereoselective versus regioselective. Regioselective means a specific region. So that's more Zaitsev versus Hoffman. That's more Markovnikov. So you're going to form one area preferentially over another, where stereoselective, that's specifically talking about one enantiomer over another. Okay, that's actually going back to stereo selectivity in the stereoisomer world. But again, those are things that I hope when I mention them, little file pops up so that you can use those terms correctly. Last but not least, radicals, which we are going to study this semester more in detail, is formed by homolytic cleavage of a bond, which means one electron goes to each. And the one that we're most familiar with is heterolytic, and that's when you create ions because the electrons stay together. Okay. And then again, I always have mantras for everything. So there is always two answers in organic chemistry. Sometimes it can be both, but usually they're competing. But the answer is usually because of A, steric hindrance, or B, stability or the electronics. So what are the two answers in organic chemistry? Sterics and electronics. And we can usually narrow most reactions and why they're doing things down to those two. All right. I then went through and made you a great big table, okay, for substitution and elimination. I talked about the characteristics of the substrate, what's going on with the kinetics. I talked about the stereochemistry and the regiochemistry, what kind of solvents, and what is favoring these. So remember, this was, wow, long time ago in the first semester, but it's not like you have to be an expert at it, but you have to know why you would do a reaction, but I wanted it in one spot for you. All right, here's the key. Here's the key. I need you to be able to look at these reactions or look at any reaction and make a pretty good educated guess. This is what's happening, and this is what I would use. So here, if you'll notice, it's very, very generic. So this is the first practice problem. Oh, look, I have a leaving group. Okay, so I have a secondary leaving group. Usually that's an alkyl halide. And I didn't tell you what was going on right there, but I did give you the product. So I went from a secondary leaving group to an inverted nucleophile. All right, that should really be screaming. Ooh, I had a secondary leaving group and I put a nucleophile in and it was inverted. This is SN2. Okay. On the answer key, I go a little bit more detailed than that, but that's what I need you to pop. Okay. That's what I need you to really recognize. So let's take a look here. I have a secondary leaving group. Oh, and I made an alkene, so I know I eliminated. But how? Okay, what kind of regiochemistry? A file should open, and I could have gone here or I could have gone there, and I made the Hoffman, which means I didn't make the most stable. I must have used steric hindrance, so I must have used a sterically hindered strong base. All right, now keep in mind, I'm pulling those right off the top of my head. You have your reference sheets, but I need it to be mostly at the top of your head. Okay, you don't have to know every detail exactly, but I do need you to be able to go, oh, that went from a secondary leaving group to an alkene. Oh, yeah, that alkene isn't the favored one. That's what I need you to be able to do because you can go look up the conditions, but you have to recognize what conditions you're supposed to be looking for. Let me do just another one. This leaving group is also a secondary leaving group, and this put a nucleophile on, but with no specific stereochemistry. So how do you do a nucleophile substitution without specific stereochemistry? This must have gone through an SN1. But wait, Jolly, you told us secondaries. Okay, so remember secondaries are the fence setter, but the way I drew it right there, that had to have gone through an SN1. Oh, you know what? One more. There's my secondary leaving group. Aha, look, I have elimination again. Okay, I have elimination. This time my major product is the Zaitsev product. So this one must have gone through just a strong base. So this one looks like it was E2. And where's that other elimination? So this also looks like an E2. Okay, because if I'd gone through an E1, I would have gone through a carbocation and it would have gone through a different pathway. And last but not least, oh, look, I'm just having fun. I'll do them all for you here. Okay, this is an alkene, specifically a transalkene. And it is going to, oh, two things. So something was added. And if you'll notice, this A and this B are opposite. So that's sin addition. So that is sin addition. All right, so I hope this page helps you just look for the generics. And I tried to put an example of pretty much, everything that we saw in the first semester. If you don't look at that and go, oh, hey, I recognize that as oxidative cleavage, this is a place to really start because we're really going to need those basic reactions. Okay, this is supposed to be from last semester. Are you going to spend all your time trying to relearn these? No. So we don't have, tons and tons and tons of time to do the review, but this page right here is a biggie. Okay? And you can work on them throughout the semester too. It's not like they have to be done immediately. And then we're going to be talking about functional groups again this semester. So we ended with alcohols. So we have talked about alkanes, alkenes, alkynes, kind of about benzene, but not in depth. And then we talked about alkyl halides, ethers, and alcohols. So this semester, we're going to cover the rest of the functional groups. And when we're done with the functional groups, you will have an arsenal of reactions that you can now use for whatever purpose you need. Synthesize new things, break it up. Okay, there's the goal for the first portion of the semester. So we have seen this one, this one, this one, that one, that one, that one, and actually, those are the ones that we've seen for the first semester. Okay, what I've done here for a review is, all right, here's the functional group. Here's the file that should open up when you hear that functional group or you see that functional group. All right, functional groups can react basically in two different ways. They can be nucleophiles or electrophiles. Okay, use its electron density to attack, that would be a nucleophile, or it can attract density, and it can be the electrophile. And don't forget, there's only two answers in organic chemistry. All right, hydrocarbons. They come in three forms. You can have straight change, you can have branch change, you can have cyclics. Okay, if it contains the maximum amount of hydrogens, it is called saturated. If it does not, it's called unsaturated. And remember, unsaturated means it has either pi bonds or rings or both. And then terminology, primary, secondary, tertiary, quaternary carbons. That also goes for alcohols and it also goes for alkyl halides. Oh, don't forget our favorite cyclic alkane, which is cyclohexane. And I did this nice little review for you. It's axial equatorial. All right, stability. Straight and branch chains are based on torsional strain. So remember, this is Newman. So if you want to know if a straight or a branch chain alkane is very stable, you would look at this eclipsing, okay? Eclipsing versus staggered. That is torsional strain, okay? When you get into the cyclics, you have to look at, okay, you have to look at the torsional, okay? So you're going to still have that eclipsing, which is only on adjacents. You're now going to add angle strain, and you also are going to have transannular strain, which is across the ring, okay? And that one happens to be called a diaxial. Not going to be using cyclohexane a ton this semester, but there's just a review of the basics. All right, alkanes, they're not very reactive and they're not supposed to be very reactive. The one that we learned last semester was combustion. Literally, they were fuels. So you can take an alkane, you can burn it in the presence of oxygen, and you will get out carbon dioxide and water. And here's specific. So this one's methane plus oxygen. gives you carbon dioxide and two waters plus heat. Okay, so that one still goes. That one still goes. Alkanes can also be converted to alkyl halides using radical halogenation. Okay, that's this semester. In fact, that's the first chapter that we're going to start after our review. All right, so it can be converted to an alkyl halide, and then it could also have a substitution with polys. Okay, so these go pretty much together. And my example here is I have three carbons. There's the conditions for radical halogenation, and you can put it there. You could put it there, but you also have the either good or bad possibility of putting more than one halogen on it. Okay, and so this is the radical chapter that we're going to be talking about. And of course, alkanes are not soluble in water and they float because they're less dense. All right, quick review of our alkenes. Generic alkenes. Hey, look, these are away from each other. So you could call this one terminal and you could call that one internal. But what we're really going to dig for this semester is conjugated systems that's a little bit more stable. And then generically, what is the stability? Notice none of these are conjugated. Okay, these are just generic alkanes. So Zaitsev's rule says mono is the least stable, and then di, and then tri, and then tetra. So Zaitsev says the most substituted is the most stable. But when you're in the di-substituted realm, remember if they're adjacent, it's called vicinal. And if they're on the same carbon, it's called geminal. And because of sterics, trans is better than cis. And then just overall, the geminal is usually more stable. Okay, so there's just a nice rule of thumb. All right, stability based on Zaitsev's rule. Okay, now here's the first interesting thing. Hey, can alkenes be nucleophiles? Yes, because they have a pi bond. Can they be very good electrophiles? No, because they don't have even a polar bond. And acid base, the pKa of that hydrogen is clear up there in the 44. So really, all they're going to do is act as a nucleophile, most often an addition reaction. Oh, look, and then I gave them to you. There's a generic addition reaction, and you can get really forceful with them, and you can do oxidation, specifically oxidative cleavage. Okay? And then selective versus non-selective. When you break the bonds, can you stop at an aldehyde or do you have to go on to a carboxylic acid? Solubility, again, they're nonpolar. They don't like water and they tend to be lighter than water. Oh man, look at that mess of messes. All right, here is all of the reactions that I gave you on the reference sheet. I know it's lumped like this. You're going to have to do it on, a few other pieces of paper. And let me see if I can get to, nope, not that one. All right. Really briefly, here's the reactions that we talked about last semester. So for your alkene, you should be able to give it, you should be able to give it a name. You should be able to do the conditions and the products. Okay. And then the type. All right, so if I say hydrogenation, these conditions are supposed to pop up. An alkene under those conditions will give you an alkane, and this is syn addition. Okay, so that's the mechanism that's supposed to pop up. So for each of these, there is a note card. So last semester when you got your reference sheet, all of those note cards, these are all listed in two different ways. Great reference to be carrying around with you. But I try and put one of these examples on that practice. So this is the one that we learned last semester, HX. Okay. Do I have enough room? Let me erase this. All right. So this, if you do hydrogenation, you get the hydrogens on the same side. If you do HX first, you go through a carbocation. Anytime you go through a carbocation, look out for rearrangement. And then the X goes on and it has no steric hindrance, or sorry, not steric hindrance, it has no preference, it's flat. So there is going to be a racemic mix. This one is from this semester. Okay, I showed you a way to make a Markovnikov. Okay, remember Markovnikov is the most stable carbocation. So that was a Markovnikov alkyl halide. Well, if I give you a way to make a Markovnikov, I need to give you a way to make an anti, and that is done with radicals. And so that's one of the reactions from this semester. So this one would give you that one, where this one gives you the Markovnikov. All right, our halogenation would break the pi bond and put, oh, I should have put an X, but I put a bromine in the anti configuration. Okay, so this one is anti-dihalide. What if you have a competing nucleophile? The second one that goes on is going to be an OH, and so that would be a halohydrin. So this would be converted over to an OH. Hydration, basically you're breaking it with an acid and putting water on it. Same mechanism. First, I'm going to break, go through a carbocation intermediate, and then the water will go and attack the carbocation. Hydroboration, if I give you a way to make a Markovnikov alcohol, I need to give you one to make an anti-Markovnikov. So these two right here are ways to make the Markovnikov. The problem with this one is it goes through a carbocation. And carbocations can rearrange. This one does not go through a carbocation. So oxymercuration, demercuration will only give you the Markovnikov that you want. Hydroboration, remember the boron square, will give you the anti-Markovnikov. All right, I'm using these terms, boron square, things like that. How deep do you have to go? If you can just do the reaction, if you can say, oh, I'm going to go from an alkene to a Markovnikov alcohol using oxymercuration, demercuration, I don't need you to be able to give me the exact mechanism. If those terms are completely foreign, a nice little review would be in order. All right, epoxidation. We talked about this one in the oxidation chapter. Epoxidation occurs with a peroxy acid and RCOO, and you make the epoxide and you get both. You get top plus, since you have no control, you can make the epoxide from the top or the epoxide from the bottom. Dihydroxylation, you can use osmium tetroxide. Remember, it's syn addition or potassium permanganate, but you do have to go cold or it'll go on. Okay, so what happens if you go on? That's this one right here. It'll actually cleave through. Cleave, and it puts a carbonyl in its place. And here's what I'm talking about, selective versus non-selective. KMNO4 is not selective, so it will go all the way to a carboxylic acid, where ozonolysis is selective, and it would have stopped. Okay, so selective versus non-selective. This one is in our radical chapter, so we're going to see that this semester. And sulfonation and hydration. Where'd you go, hydration? This one and this one are the same. If you want to stop and put the SO4 on, it just has to be under cold temperatures. Okay, so those are basically the same reaction. And can you really stop and put the SO4 on there? It's very difficult, but technically. All right, so there's your alkenes. Oh, conjugated alkenes are this semester. Okay, we have a whole chapter. All right, so there is the review of your alkene reactions. Since we're here, let's just do your alkyne reactions. All right, if I said hydrogenation, okay, this would be syn addition. And if you do not stop it, if you don't poison it, if it's not selective, you're going to go all the way down to an alkane. If you do use a poison catalyst, you can be selective, but you are stuck with syn addition because remember it sits on the metal catalyst. All right, DMR, we did do this one last semester, but that is a radical reaction. DMR, dissolving metal reduction, is the only way you can get to a trans because it goes through a radical mechanism, not an ionic mechanism. All right, hydrohalogenation would be just like the alkenes. First, you form the carbocation. And whose carbocation? You form the Markovnikov. And then the X would come in. But there's two pi bonds, so you would do it twice. So geminal dihalide, the two halogens would be on the same. If you do direct halogenation, you just put halogens everywhere. Oh, look, hydration. Remember, the alkyne's a little bit more difficult. So when you do hydration, we throw some mercuric sulfate in there, or something to help. But that's the one that I have on the sheet. Oh, your first step is the formation of an enol. So right here, it's the same mechanism. Okay, right here, I have broken the pi bond and I've put my hydrogen on, and my nucleophile is going to be water. But guess what? I have an OH on an alkene, and that really doesn't exist. That is really a ketone or a carbonyl in disguise. Okay, so there's hydration of an alkyne. Hydroboration, okay. You actually cleave through. Oh, look. Sorry, not cleave. You actually go through an enol, and if it's internal, it'll make a ketone, and if it's terminal, it'll make an aldehyde. So kind of the same idea as that mechanism. Do not forget if you have a terminal, that is a pKa of 25, and you will always rip off the hydrogen with a strong base. And remember, I love that as a nucleophile. So that's my acid base, don't forget. And then in the oxidation and reduction chapter, we saw, ozonolysis if you cleave, or KMNO4. The key here is if you cleave through three bonds, you have to replace three bonds. So you're stuck with carboxylic acids no matter what you do. And this one can be oxidized further into carbon dioxide. So if it's terminal, I generally jump straight to this or this one. I try and be consistent, but I'm not. I'm sorry about that. So that one in CO2, just know that terminals can cleave off into CO2. All right, alcohols will be in a different lecture. All right, so we did our alkanes, we did our alkenes. One note before this one is done. Aromatics are not alkenes, but they do contain double bonds. This has an entire chapter, okay? So this is second semester as well. We learned a few reactions in the oxidation chapter, so we're not going to forget those, but there's a whole chapter on benzene. And last but not least, the alkynes that we saw. Hey, are they reactive? Yes, because they contain two pi bonds. Electrophile? No, because there's really nothing to lose. And yes, watch out for acid base if there is a terminal. And so these are the reactions that I just did on the other page. Solubility, again, they're nonpolar, so they don't like water, and they're also light, so they float. And oh, look at that fun. Look at that fun one. All right. That is a very fast review of your hydrocarbons. So again, it's the generic idea. I'm not asking for detailed mechanisms. I'm talking that, hey, if I wanted to use an alkyne, how could I get to A? That's the generic. And I know that's very vague, but you just need a whole bunch of mechanisms and reactions in your arsenal. And the only way to do that is a whole bunch of practice. So please don't take this as an overwhelming, oh, work through every problem right now, but pull out those note cards, start testing yourself. Okay, if I wanted to get an anti-Markovnikov alcohol, what would I do? And that's called retrosynthetic. Okay, so just generic, and then of course we will practice later on. All right, that is the review for the hydrocarbons. Until next time, jolly out.